reactions that only go in one direction. Um, but but it turns out that most reactions don't go in only one direction. Most reactions are reversible and they don't go to completion. Um, okay, so let me think. For example, most acids don't dissociate completely, right? So this is what differentiates strong acids, which will disassociate completely into their H plus ions and the counter ion from weak acids, so like vinegar. So in a weak acid, only part of the acid actually will split up into the H plus and the other ion. Let me think of some other. So yeah, and weak bases are the same. Okay. So there are several industrial processes that are also equilibria. So for example, does anyone know how much most of the world's fertilizer is made? So, before the industrial era, um, they would use like natural products as a fertilizer, so manure, poop, um, right? But you can only grow so much food using only natural fertilizers. So in the 1910s, 1920s, in that era, a German scientist named Fritz Haber developed the Haber-Bosch process. And the Haber-Bosch process takes hydrogen gas, which is easily made from natural gas or water, and nitrogen gas, which is freely available in the air. And he developed a way to combine these chemicals to make ammonia, so NH3, which we've seen in previous lectures before, that chemical. And it turns out it's quite difficult to actually do this because the nitrogen-nitrogen bond is very strong. So it's very difficult to actually make ammonia industrially. So he found a way to do it in the 20s. So this ammonia can be readily converted into other forms of nitrogen. For example, nitric acid, so nitrates, so nitrate salts, which so that gave this process a great usage in military applications because you need nitrates to make gunpowder. And also you can turn it into ammonium salts, so ammonium chloride, for example, or you can make other nitrogen-containing substances which are easily used as fertilizer. So so this process is mainly responsible for the you can think of it as basically responsible for the explosive growth of China's population during that time period, following that time period. So China used to be like a very it's not used to be more sparsely populated, so very poor, since they weren't able to actually just make the food to support a large population. But following the invention of industrial fertilizers, they could easily support a very large population to grow like rice and stuff like that. Well, it turns out that the process of converting hydrogen and nitrogen to ammonia is also in equilibrium, and it's a reaction that doesn't go to completion. So chemical engineers put a lot of work into making the reaction go as far to completion as possible, because if you can make the reaction go towards the ammonia side to make more ammonia, then it's more efficient. You don't need to put in as much hydrogen and nitrogen. So there's a lot of work that goes into making the process more efficient. Okay. So last class, we discussed reactions that only go in one direction. So so what happens if the rate of reaction in one direction is equal to the rate of reaction in the reverse direction? So like what happens if A going to B happens at the same rate as B going to A? then that means that there will be no net change in A and B. So there's no net change, so the system is what we would call in equilibrium. So you can see in the picture, we have A reacting to form B. So you can see that the concentration of A will decrease over time, whereas the concentration of B increases over time. However, eventually you reach a point where there's no net change in either A or B. So here the system has reached equilibrium. Obviously here, there's still a lot of change going on, right? Because you can see A is rapidly decreasing, B is rapidly increasing. So this part is not in equilibrium, okay? So this is why we call this dynamic equilibrium, because movement is still going on, but we don't see a net change. So for example, a very common example would be dissolving salt in water. So if you ever try to dissolve a lot of salt in water, you might know that you can only add so much salt to water. And at some point, no more salt will dissolve. That doesn't mean that nothing is happening. So some of the ions in the salt, in your table salt, are still going into the water. But what's happening is that the ions are going into the water and the ions are coming out of the water at the same rate. So overall, you don't see a net change. Okay, so this is all nice, but this is all qualitative. So sometimes we would like to make predictions about how far the reaction will go forward and how much stuff will be present. It's very important. Okay, so we're going to quantify equilibrium. So consider this reaction. We have A. So A components of, so this is like the number in front of the chemical. So we have a chemical A with the number in front of it A. So this many, so little a is how much A's are going into the reaction, plus B, and then uppercase B goes to C times chemical C and D chemical D, okay? Then we can write this expression, so the concentration of C raised to the coefficient C. So C is a bad example. So let's look at D. So we have the chemical D, and it's in brackets. So the brackets represent the concentration of D. Okay? So the concentration of D raised to the coefficient D, which is the same coefficient as here. And then, so we start with the products and we do that. So we do this multiplication of the product terms. And then we all divide that by the reactant terms. So we have the chemical A, the concentration of A raised to the A power, so this coefficient A here, and then the concentration of B raised to the B power. Okay? So when the system is at equilibrium, we have these concentrations A, B, C, and D. And when we do this calculation, we get this constant called the equilibrium constant. And it turns out that if we change the concentrations so that we get a different equilibrium, this constant will still equal this constant. This constant will hold true for any situation at a given temperature. The constant will change with temperature. And when we discuss thermodynamics, we might see how the constant changes with temperature. So how was this discovered? So back in way back in the late 1800s, probably, I think. So some scientists were investigating the reaction between, I think, sulfur dioxide and oxygen gas and sulfur trioxide. And they found that this what we would call reaction quotient would remain a constant at equilibrium. So we can calculate this number at any state. It doesn't have to be an equilibrium. So this we call it the reaction quotient. Okay? And the reaction quotient is very important because the reaction quotient can tell us which direction the reaction will go. So if the reaction quotient, so let's say this direction, the direction the arrowhead points is forward, and the reaction in the other way is called backwards. We'll just call it that. And by the way, most often you will see this as a double-headed arrow. This really should be a double-headed arrow. You have one arrow in this direction and the other in that direction, but I can't easily type that, so we're just going to use the single arrows for now because they're easier. Okay, so if the reaction quotient is larger than the equilibrium constant, which direction do you think the reaction will go? Do you think it will go forwards or backwards? Anyone? Just take a guess. You'll have a 50% chance of getting it right. Great. So if we have a large reaction quotient, that means that the numerator is going to be large, right? So if the numerator is large, that would indicate we have high concentrations of reactants. And then we need to make the numerator smaller and the denominator larger to bring the reaction quotient back to the equilibrium constant. And this would require the concentration of A and B to increase while the concentration of C and D decrease. Hence, the reaction will go backwards. So great. Likewise, if the reaction quotient is smaller than the equilibrium constant, which direction should it move in? If we have a very small reaction quotient. So it will go forwards, right? Because we have a very small amount of products. Okay. And I want to give you some notation issues. So sometimes we consider equilibrium using gases in the gas phase. So all of your products and all of your reactants are gases. In this case, we can either use concentrations or pressures, and both are equally valid. However, I think pressures are usually better because, so side note, strictly speaking, these are not supposed to be concentrations. The concentration is an approximation for something called chemical activity, which you don't need to worry about. And the chemical activity of a gas is usually defined, is approximated by its pressure. So I think it's better to use pressures instead of concentrations, but you can convert in between them, so it's fine. Yeah. And so if we have a pure solid or a pure liquid, so for example, if you have something dissolved in water, like the water could be like a pure liquid. Or if we have like some sodium chloride, that would be a pure solid. So these are not usually included in the equilibrium expression because their chemical activity is defined to be 1. So, you know, if we have 1 in this expression, it just goes away, right? 1 is the multiplicative identity. Another note that I just wanted to quickly mention is that the equilibrium constant is dimensionless. So let me spell it out. So although A, B, C, and D are in units of like moles per liter or atmospheres or something like that, and they don't necessarily all cancel out, by definition, the equilibrium constant will always be dimensionless. So there will not be units, okay? So dimensionless. Okay, and can everyone just write down this equation? Because this is law of mass action is very, very important. Or if you can figure, if you know how to derive it, you don't need to write it down. Okay. So let's just do one example. Or not. What? Okay. So I'll just do the first one, and then I'll let you do the other 4. So we want to write the reaction quotient expression. So the form that the reaction quotient will take. Okay, so we have, so phosphoric acid dissociates into the phosphate ion plus 3 hydronium ions. Okay? So this is a pure liquid, right? And because it's a pure liquid, the water is a pure liquid, so we can ignore it in the expression, right? So ignore that. So now we have to consider this. Let's do the products first. So can someone tell me what the numerator should be? So the numerator is in the form, so concentration of phosphate times the concentration of HLEO plus and raised to the power of X and Y. So this is the numerator. So can someone tell me what X and Y are? So remember that there's a 1 here. It's just that the 1 is implied, so we don't include it. Well, let's look at phosphate. Yeah, so if we look at phosphate, you can see that the coefficient in the front is 1. So we drag that 1 over here, and we can see the coefficient here is 3, so we drag the 3 over here. So that's the numerator. What about the denominator? Can someone tell me what the denominator is? So we ignore water, but we have this to contend with. So what should we put there? Great. And of course, it's to the 1 power because there's a 1 here, but we can just ignore the 1. So therefore, we have our reaction quotient Q equals the concentration of phosphate times the concentration of hydronium to the 3rd power divided by H3PO4. Okay. So I want you to do that for the other 4 examples. So here. So can we just spend 5 minutes to write the reaction quotients for these? And post the answers in the chat once you have them. Just do these 4. I did the first one already. There is one thing I would like to mention. For a gas, you might see a gas written like this, where it's in parentheses. You might see this or this, something like that. So these both mean pressure. So just something to keep in mind. So can someone tell me the answer to the first one? So, I mean the second one. So N2O4 goes to 2NO2. So can someone tell me what the numerator is? Oh, okay, great. Can someone else do the third one, maybe? Can someone else do the third one? So what's the third one? Yep. What about the... And it should be in, yeah, just to clarify, make sure you're putting it in brackets when you actually write it out by hand. I guess in the chat it doesn't matter since it's hard to type anyway. What about can someone else do the fourth one? Fourth one here. Yep. And then what about the last one? So remember, we don't include solids, pure solids or liquids in the equilibrium expression. So for the last one, it should just be CO2, right? Since calcium carbonate and calcium oxides are both bulk solids, so we don't need to include them. And while we're on the subject of reaction quotients, I think I want to introduce an idea that we will probably talk about a little bit later. It's not, let me clear the annotations first. So something called, Le Chatelier's principle. Okay? And basically, the idea behind Le Chatelier's principle, or Le Chatelier's principle, is that if you have a system and you apply some stress on that system, then the system will move in a direction to minimize the stress. So that sounds a little bit complicated, but for example, let's say we have A goes to B, and then we have some balance. So imagine a seesaw with some amount of A and some amount of B. So let's say we apply some stress to this system. So we add more A. Let's just say this. Okay, so we applied some stress on the system, and now it wants to tip in this direction. So the system will respond to this stress by converting some of the A to B, so that we get this. Okay. So if we add some material to a system, the reaction will move in a direction that will bring the reaction quotient back to the equilibrium constant. So we want the reaction quotient, so we want it to equal the equilibrium constant. So the reaction quotient Q equals big K, sometimes with an EQ subscript. Okay, and this is kind of funny. So Le Chatelier's principle actually turns up in economics. So economists have kind of stolen Le Chatelier's principle to discuss economic systems. And we will talk about this a little bit later in future lectures. I think with thermodynamics probably. Okay. So let's just talk about a qualitative understanding of the equilibrium constant. So if K is very large, then we can say the reaction is favorable because a lot of the reactants are turning into products. If it's very small, then the reaction probably is not super favorable because very little of the reactants are actually turning into the products. So for example, combustion reactions often go to completion because they have huge values of K. So for example, the combustion of hydrogen and oxygen at room temperature has a value of equilibrium constant like 10 to the 30th power. Okay, so some ridiculously huge number. A lot of electrochemical reactions will have equilibrium constants in the range of like 10 to the 80th power, for example. So really huge numbers. Some reactions have very small values of K. For example, so the dissolution of mercury sulfide has a K of like 10 to the minus 80. Okay, so yeah, so that would be a very unfavorable reaction. And I do want you to note that the size of the value of K does not impact the rate of the reaction. So for example, who has ever seen a diamond, right? Well, if you've, diamonds actually will turn back into graphite, so the stuff in pencils. And this reaction is favorable. It has a K of 2.24, so not super large, but it will still happen. So diamonds will turn to graphite at room temperature. But no one has ever seen a diamond turn to graphite because this reaction is immensely slow. It's too slow to happen at any measurable rate. So so I just want to emphasize that the magnitude of the equilibrium constant has nothing to do with the rate. For example, you might have a rock at a very tall mountain, on a very high mountain, and the rock rolling down the mountain will be favorable. Gravity will pull the rock down the mountain. However, if the rock is like on a flat surface at the top of the mountain, it's not going anywhere, right? That's a metaphor, okay? So just a note on reactions involving gases. So strictly speaking, you should, I think it's better to use pressures for gases, but you can use both. So remember the ideal gas law, PV equals nRT, right? Well, concentration is given in moles per liter. So moles corresponds to N and liters corresponds to V. So we can rearrange the equation as P equals nRT over V. Yeah, so that means if we want to convert from Kc to Kp, we need to multiply N over V by RT. So we need to multiply the concentrations by RT, some arbitrary amount, okay? So we get this formula, so write this down. So Kp equals Kc times R, so R equals 0.08206 times T times delta N. And what is this delta N term? This delta N term corresponds to the change of molecules of gas, change in the number of molecules of gas. For example, with this reaction, we have one molecule of nitrogen so one molecule of nitrogen plus 3 molecules of hydrogen goes to 2 NH3, so 2 molecules of ammonia. So we have 2 molecules on this side and 4 molecules on this side. Thus, the change in the number of molecules is -2 because we're going from 4 to 2. So 2 minus 4 is -2. So if the Kc equals 50 at some arbitrary temperature, can you calculate Kp? Oh, you need the temperature. 500 Kelvin. At 500 Kelvin. Can someone calculate Kp? Kp. So does anyone have it? So can someone tell me what Kp is? Just plug the numbers in the calculator, right? So we know Kc. I gave you Kc. So Kc is 50. Can someone tell me the value of R? Right, 0.08206, because we're working in liters and atmospheres, so we need that form. And what's delta N? I already told you the value of delta N, right? So in this case, we're going from 4 molecules of gas to 2 molecules of gas. So the number of gas molecules is decreasing by 2. So the value of delta N means change in N, by the way. So that's what delta usually means, the triangle. So it's -2, right? So 50 times 500 times 0.08206, and that's raised to -2 equals 0.0297. Okay, let's work with some slightly more difficult problems, okay? So I want to introduce the idea of an ICE diagram. So initial change in equilibrium. So consider we have this reaction. So we have AA, BB, C. It's the same thing we saw before. And I wanted to find some initial concentration. So let's just say we mix some amount of A, B, C, and D. We just mix it with some water and see what happens. So our initial concentrations are going to be A0, B0, C0, and D0. Okay? So let's say that this reaction goes forward by some value X. That means that the change in A will be X times A, right? Because for every one reaction unit that goes forward, the A will be decreased by A. The concentration of A will be decreased by this coefficient A. Hence, we can write the change as minus A times X. And the same logic applies for minus B times X. And of course, we're going to assume that we're producing reactants, but it really doesn't matter since X can be negative. So this goes forward by 1 unit. This reaction goes forward by 1 unit. So so we get the concentration of C increases by coefficient C. So we have plus Cx and plus Dx. Oh, I made another typo. This should be plus Cx. Therefore, the equilibrium value should be the sum of these two. So we have initial and then minus the change. So plus the change. So A0 minus AX, and I don't know why I made the typo there since I didn't make the typo in the combined version. Plus. So A0 and then A minus X and then B0 and then B0 minus X and then C0. So C0 plus Cx and D0 plus Dx. So why is this useful? Well, now we have the equilibrium concentrations. And remember that at equilibrium, the reaction quotient equals the equilibrium constant. Therefore, if we know the equilibrium constant and we know the initial values, we can calculate the final values. And we get this rather messy equation here, but you can solve this using a graphing calculator or something like that. So this is easily solvable using a graphing calculator. And then we can solve for X, and this will actually tell us how much this reaction will go forward. And then of course we can just plug X back into these expressions to give us the equilibrium concentrations. So I think you might want to copy down this ice diagram just so that you know how to construct an ice diagram. Okay. So everyone knows that this should be a plus, not a minus. Right? Okay, great. I'll just do one example. This one is a little tough, so I will do it out for you. So let's say we combine 3 moles of hydrogen and 3 moles of oxygen, and we add this to a rigid 25-liter container. So in other words, the volume of the container will not change. It's constant, 25 liters, at 1,500 Kelvin. So very high temperature. So if I remember correctly, steel will melt at about 1,800 Kelvin. So this is very hot. So everything is going to be gas phase, so we don't need to worry about that. And I want to calculate the equilibrium pressure of water, and we're giving the Kc equals 67, which is a random number I picked. It's an estimate I made. It's not exactly 67 at that temperature. So because I didn't want to have to do the calculations, but okay. So we want to find the pressure of water. So there are 2 ways to approach this problem. Either we can calculate the concentrations and then simply convert concentration to pressure at the end, or we can calculate, or we can convert all of the concentrations now into pressures and then just solve it. And it turns out that converting into pressures first has more steps, so we're going to do it that way because I want you to have some practice with the intermediate steps. So the first step is to convert Kc into Kp since we want pressures. So, let me copy down the data. "25 liters, 1,500 Kelvin, and then, yeah. Okay, great. So this is the double-headed arrow I was talking about earlier. So this is really how you should write it, but I can't do that on the computer, so yeah. Okay, so let's convert Kc to Kp. Kp equals Kc times Okay. So R is equal to 0.08206, and I'm not including units for now. Then times 1,500, and then what's delta N? So we're turning 3 molecules of gas, so 2 hydrogens and 1 oxygen, and we're creating 2 molecules of gas. So we're going from 3 to 2, so 2 minus 3 is -1, so delta N is -1. And then this equals, let me see what it equals, can't remember, times, and this equals 0.544. So this is the value of K that we're going to go for. Now, what's the equilibrium constant expression? The reaction quotient. So this equals, so the pressure of H2O. However, we have a coefficient of 2, right? So this should be squared. We drag the coefficient over to the exponent, and then repeat the same thing here. So remember, the reactants go in the numerator. So pressure of H2. Right. We have this is Q, and we want to calculate we want to find this at equilibrium. So this equals Kp, which equals 0.544. Now, we need to calculate the pressures of Now we need to calculate the initial pressures of H2 and O2. So we rearrange PV equals nRT to get N over V times RT. And this calculation is fairly straightforward. So 3 over 25 times R times T equals and notice we have the same amount of hydrogen and the same amount of oxygen. So the pressure of hydrogen and oxygen are going to be initially equal. So we can set up our ice diagram. So, okay. So we have an initial pressure of 14.77 atmospheres. Oh, let me get a better view. So, and then here we also have 14.77 atmospheres. And then we start off with no water, so we just put a fat 0 there. A donut, as the math team coach in middle school would say. So a donut. Okay. And then the change. So let's say that this reaction, go back here. Let's say this goes forward by some value of x. So can someone tell me so the change of hydrogen is going to be, so we're consuming 2 hydrogens for every x that we go forward, every unit of this reaction that goes forward. So minus 2x, and then plus, and then this is minus x, and this is plus 2x, right? And then, so this is going to be 14.77 minus 2x. And then notice these are going to be our equilibrium pressures. So we plug that back into here. So this goes into here. This goes into here. And this goes to here. So we get this equation. We have this equation here equals Kp. And everyone knows how to solve the quadratic equation, right? Well, this is just a quadratic equation, and so you can solve it. But I have a very nice graphing calculator. I have a really fancy calculator, so Let's just see what the calculator says. So we get that x equals 5.15. Okay? And the problem statement asks us to calculate the pressure of water. So recall that the final pressure of water is 2x. So therefore, pH2O equals 2x equals 10.3. 10.3 atmospheres. And that's it, okay? Do I have any questions on how I solve this problem? Is anyone confused on any of the steps here? Wait, why don't the chat open? If not, then what I think we should do is I can give everyone, how about 20 minutes or 10 minutes to do this problem. So this one. Can we have 10 minutes to do this problem? And then after that, we'll take a break, okay? So basically, I'll come back in 10 minutes. 10 minutes, I will show you how to do the problem, and then we'll take a 10-minute break, okay? I'm just gonna do it real quick. Wait, so does anyone have an answer? Okay, it seems not, so I guess I'll just do it. So everything's 1 molar, so that's nice. So let me just write that down. And then H2 plus I2 double arrow goes to 2HI. Kc equals, oh, that's messy, 45.9. Okay, and calculate the concentration of HI. So let's set up the ice diagram. Our reactants go here, and our products go here. Can someone tell me what goes here in this region? What should go there? Oops, why did that happen? So what goes here? What's the initial concentration of hydrogen? I wrote it here. It was 1 molar. So we put a 1 here. What about iodine? What's the concentration of iodine? One, right? Because we have 1 mole in a 1 liter container, so 1 divided by 1 is 1. What about HI? I mean, I guess I didn't explicitly say it in the question, so my bad. So yep, 0, right? Because we never said that any HI was added to the flask, so you can assume it's 0. What should I put in the change column, in the change row? What should go here? In here, so here. What do you think? Great. So if you look at the stoichiometry here, 1, 1, 2. So minus 1x plus 2x. Great. So this is 1 minus x. Okay. Can someone tell me what the reaction quotient expression is? What does this equal? Right? And then this equals, which equals? Right. What I want you to see is that we can rewrite this part. We can rewrite this as 2x squared over 1 minus x squared equals 45.9. And if we take the square root of both sides, we get 2x over 1 minus x equals 45.9. Now, can someone solve this equation? Oh, maybe you can't see. Can you solve this equation? I guess we don't have to do that. So it does, x just equals 0.96. And we need the concentration of HI, which is 2x. So 2x equals 1.92 molar. 1.9 because of sig figs. Okay. So how about we take a 10-minute break? And if you don't understand this, you should try it again, I think, because I think it's very crucial to be able to understand this. And we'll take a 10-minute break, and when we come back, I might try to find some multiple choice questions based on the SAT chemistry exam. Okay, so basically everyone's here. So I think we can move on. Okay. So I do want to show you guys how to make some approximations, because a lot of times when you do these problems, you might get these cubic equations or quadratic equations, and they're a real pain in the ass to solve. So it's often useful to make approximations to make the quadratic terms go away. So you end up with a linear equation, which is very easy to solve. So, for example, if our equilibrium constant is very small, like 10 to the minus 2, 10 to the minus 3, okay, we can assume that the concentration of reactants will not change very much. Conversely, if our equilibrium constant is very large, what we can do is we can assume the reaction goes to completion first, and then we start from the complete state and we go backwards. Okay, so I know that might be a little confusing, so I'm going to illustrate it with 2 examples. And by the way, the whole working backwards thing is not super common, but the approximations with small equilibrium constants is essential now. It's essential. Okay. So we have this reaction, so acetic acid, which I've abbreviated as HOAC. This actually equals CH3COOH. And we're given that K equals 10 to the minus 4. Now, we set up our ice diagram. What was the concentration again? Let me see. So we have a concentration of 0.5 molar, right? And 0 and 0. Now, change is going to be minus x plus x plus x. Does everyone see why that's true? Does everyone understand this step, what I've done here? Right? Now, our reaction quotient is going to equal, oh, that should be OAC. That should be OAC. So OAC minus and then this equals x times x, right? But now what I want you to notice is that because our equilibrium constant is very, very small, this reaction will go forward only a little bit. Hence, x is actually very small. X is going to be on the order of like 10 to the minus 2 or something like that. So that's just my estimation. I don't know if that's actually right. So x is going to be much smaller than 0.5. 0.5 is going to be much larger than x. Hence, we can ignore x. And then this, of course, equals 10 to the minus 4. Thus, we get x squared over, oh, my pen ran out of ink. Another one here. X squared divided by 0.5 equals 10 to the minus 4. And can someone solve this while I refill my pen? So what do we get for x? Okay, great. So I think that's, let me just double check this. Great. So, and then we get x equals 0.71. 7.1 times 10 to the minus 3. Okay, so my estimate was pretty good. And then we double check this. So 7.1 times 10 to the minus 3 is much smaller than 0.5. So our approximation is valid. Okay, and the question asked for the pH. So, and then this of course equals the concentration of H plus, but we want pH. And you should remember this definition. So pH equals negative log of H plus. Write this down. You should write that down. And then, so if we do that, we get 2.15. Okay. And yeah, and when you do logarithms, you add an extra sig fig. Just fun fact. Okay. Okay, so this is how approximations are useful, because otherwise we would have to deal with this term, which is very messy. Let's look at the next problem. So we have a reaction, 2H2 plus O2 has K equals 6.45 times 10 to the 30th power at 373. So we have a 1 liter container, 2 atmospheres of H2, 1 atmosphere of O2. What's the pressure of O2 after combustion? So now, the first step is to notice that our equilibrium constant is huge, okay? We have a massive equilibrium constant, so that means we can assume the reaction goes to completion. So, if we assume we start with 2 atmospheres H2, and then this goes to, so you can work this out yourself, but here's the equation. So this will generate 2 atmospheres of H2O. So now our ice diagram looks like this. Okay. Yeah. So plus x, and then plus 2x, and then 0, 0, and then 2, and then minus 2x. So, and then remember that our equilibrium, our quotient for this, our reaction quotient is going to equal H2O squared divided by H2. So pressures, so I put it in parentheses, right? And then notice that x is going to be very, very, very small. Like x is going to be tiny. So we can ignore it here because 2 is much larger than some tiny number. So this equals 4 divided by x squared, 2x squared. And then this can be, and this is easily solvable. Okay? So that's how you do that. So that's, I just wanted to illustrate how we can do that, but you shouldn't run into that too much. So can we do this problem? So I'll do 5 minutes. So does anyone have the pH? So does anyone have the pH? Okay. Okay. So this problem is very similar to the first example in the previous slide. So we can use the same procedure to do this one. So yeah. So I'll just simplify the procedure. Okay. So we have H plus F minus. Does everyone know how to get to here? Does everyone understand how we came up with this? Does this make sense? No. Now, looking at this reaction equation, you should be able to see that the amount of H plus is going to be equal to the amount of F minus. Hence, we can write this like this. And again, we make the approximation that the concentration of HF doesn't change. Hence, we have H plus equals X equals the square root of 10 to the minus 3.1 times HF. And that's it. Basically, that's it. So, like, if you really wanted to, I guess you could memorize this. But, okay. So, okay. So, I just want to do one more topic real quick. So, combining equilibrium expressions. So all of this is basically just mathematical manipulation, but it's good to get a feel of it. So we want to be able to reverse reactions, multiply reactions, and combine reactions. So to illustrate this, I'm going to use these reactions. A goes to B, B goes to A, B goes to C, A goes to C. We're given that this has KEQ with some arbitrary K. We need to find the equilibrium expressions for all of these. Well, this equals B, the concentration of B divided by the concentration of A, right? So do you understand? So we have this. We have the equilibrium constant for the first reaction equals the concentration of B over the concentration of A. Okay. This one, we have the equilibrium is equal to A over B, right? Now, can everyone see that this equals 1 over okay? What does this mean? If we want to flip a reaction, all we need to do is take the reciprocal of the equilibrium constant. Okay. Now let's just call this K2. And then this, of course, equals C over B. Now, let's look at this one. So we have C over A And we need to write this in terms of K1, K1, and K2. Well, and then times, if we do this, then we get C over A, which is what we want. Furthermore, this equals K1, this equals K2. So in other words, if we add these two reactions together, if we add 1 and 3 together, then we multiply the equilibrium constants. Okay? And as a final example, what about this? And then this, of course, has equilibrium constant b squared over a squared. And then this equals K1 squared. So if we multiply the reaction by some number, then we take the equilibrium constant and we raise it to that power. Okay? So, and I think this is the final problem that I'm going to go through. So we're given this data and we need to calculate this. Okay. Give me a second to copy this all down. So I'm not going to do the exact numerical calculations. I'm just going to do it in symbols just because it's the same thing. Okay. So we have these three equilibrium constants, K1, K2, K3. Now, let's start with the product side since it's easy. It's only one thing. So we have 2 N2O4. So, and we notice the only reaction here that has N2O4 is this one. However, we have N2O4 on the reactant side. We want it on the product side. So let's first reverse this reaction. Okay, so this has 1 over K2. Now, but notice we have 1 N2O4, but we need 2. So we multiply everything by 2. Can someone tell me what the equilibrium constant is? What's the equilibrium constant? What should I write here? So we're taking this one and we're multiplying it by 2. So we need to raise it to the 2 power. So it should be 1 over K2 all to the second power. Great. Okay, now we need to get rid of this NO2 stuff. So we have NO2 here. So we can use that. So what we should do is we can combine this with the reaction. So 4, wait, my bad. For NO2. And then, so basically, to get this reaction, we need to take this one and multiply it by 4. So this should be K3 to the 4th power. Okay, we're almost there. Now we need to get rid of this nitrogen. So to do that, we should use this reaction. So we need to reverse it. Wait a second. Something's suspicious. This is, did I copy something down wrong? I think I copied something down wrong. Okay. Well, regardless, okay. So we do, yeah, okay. So we need to generate NO2, so from N2O and oxygen. So we can use this reaction. I mean this one, right? Wait a second. Yeah, we need to get rid of the nitrogen. So to get rid of the nitrogen, we can use this. Oh, right. Okay. And then when we combine all of this, everything should go away. But it's very strange. I think there might be a problem with the problem statement that I found this online from, because I don't think there's a way to combine these to get the correct expression. Let me do this real quick. Yeah, that's right. So this should say 4N2 plus 2O2. And then this goes away. Yeah, I think there's this should be 2O2. Yep. Okay, so this is fine. So to get this reaction, 4N2O goes to 4N2. What we've done is we take this and we reverse it, and then we need to multiply by 2. So first we reverse it, so 1 over K1. And then we need to square that. And now we need to add these three things together, because when we add them together, everything cancels out. And we're left with this, okay? So, so this gives us K3 to the 4th divided by K2 to the 2nd times K1 to the 2. Okay, so that's it. I don't think you'll see this too much, though. On the AP probably, and definitely on any chemistry Olympiads. So, okay. But don't worry about it too much. Okay, so how much time do we have left? We have 10 minutes left. So I think now would be a good time to, let's look at some multiple choice questions. There's no need to do the math here. So I have here a book. So this is for the, okay. So I think that one other thing that is probably relevant to the SAT chemistry exam is called the KSP. KSP. So solubility product. Let's consider a reaction. Anion and a cation goes to A minus plus C plus. So we have a salt, an ionic compound dissolving to give an anion and a cation. Okay? And then we can write this okay, and why don't I put coefficients here? So alpha and gamma. We'll use alpha and gamma. Alpha and gamma. So this is the solubility product formula. So for example, if we have barium sulfate, KSP would equal okay. And it turns out that when you dissolve a salt, when you dissolve an ionic compound in water, you cannot have this product, this so-called solubility product, be greater than KSP. So as soon as this as soon as this product increases enough to be greater than KSP, a precipitate will form. So a precipitate. I don't think I have a good picture, but you can think, but yeah. So for example, let's look at the problem. Let's look at a problem here. Let me see if I can find a KSP problem. Okay. So we're given that so let's look at radium sulfate. And we're given that KSP equals 4 times 10 to the minus 11. So we need to calculate the solubility of radium sulfate. So when we dissolve the maximum amount of salt in water, then this product should equal KSP. So we have that radium 2 plus times the concentration of sulfate equals KSP. And what I want you to notice is that when we look at the dissolution reaction, we produce 1 mole of radium for every mole of sulfate. Hence, the concentration of radium should be equal to the concentration of sulfate. So therefore, we can say that X squared equals KSP. So we solve for X, which gives us the concentration, and then we can multiply this by the molar mass to give the solubility. Maybe we can look at a different example, a slightly more difficult one. So consider the solubility of iron hydroxide. Okay. And then we're given that iron 3 hydroxide. And then we are given that this I don't know, that should not be in parentheses, but I can't erase pen. So we have KSP equals 10 to the minus 31. Okay, that's a made up number, by the way. I think it's close to accurate, but it's around 10 to the 30 range, but I'm not sure exactly. So we have this. So we want to calculate the solubility of iron 3 hydroxide in grams per liter. Grams per liter. So our KSP expression should be OH minus cubed okay? But we have that, notice in this reaction, for every mole of iron, we have 3 moles of hydroxide. So therefore, the concentration of hydroxide is going to be 3 times the concentration of iron. So we can write this as 3x cubed times x equals KSP, right? And then you can solve this, and we find some value of x equals something, and then we simply multiply this by the molar mass to give grams per mole. So let's do how about you guys do an example? And then I think after that, the lecture is probably going to be about over. So let's do copper iodide and KSP equals, let me look at the KSP. I think it's 10 to the minus 10, something around those lines. So, okay, so Ksp is 10 to the minus 12. Can you give me the solubility in grams per mole? What's the solubility? Solubility. So 5 minutes. Expression. So what's the expression of the solubility product? What's the solubility product expression? Great. So Cu plus times I minus. And I hope you can see from the equation that I minus and Cu plus are going to be equal. And this equals Ksp. Hence, x squared equals Ksp. X equals, let me see, 10 to the minus 6. So we have the concentration of Cu2 of Cu plus, and the molar mass of copper. So that means we have this many moles per liter, right? And then we need to multiply that by so 63.55 plus 127.9. So this gives us Cui is 191.45 grams per mole. So therefore we can, so times 191.5 grams per mole. So 191.5 grams per mole. And then this equals, so 0.000192 grams. Okay, that's it. And I don't think I have anything else to talk about, so I guess that's the end of the lecture, and I'll see you later.